Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into Earth's most profound slumber, the era when our planet froze solid for 100 million years. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The Earth sleeps beneath a blanket of ice that stretches unbroken from the North Pole to the South Pole, covering every continent, every ocean, every familiar coastline in a crystalline shell that extends to depths measured in kilometers rather than meters. This is not the partial freeze of recent ice ages, where glaciers advance and retreat across northern lands while tropical seas remain open to the sun's warmth. This is Snowball Earth, a planet transformed into a single, gleaming sphere of white ice suspended in the darkness of space, reflecting nearly 90% of the solar radiation that reaches its surface back into the cosmic void. The sun rises and sets over landscapes that have not seen liquid water for millions upon millions of years, its light striking surfaces so uniformly white that the boundary between Earth and sky becomes a matter of subtle gradation rather than distinct horizon. Ice covers the equatorial oceans where coral reefs might one day flourish, extends across the sites of future deserts, and blankets the locations where rainforests will eventually claim dominion over steaming valleys. Every geographic feature that will one day define the planet's character lies buried beneath this comprehensive frozen archive of what Earth once was and what it might become again. It's 717 million years ago, deep within the Cryogenian period, and the planet has entered a state of refrigeration so complete that ice sheets extend across the equator itself, a phenomenon that challenges every comfortable assumption about how planetary climates operate within the habitable zones around stars. Where warm ocean currents once carried heat from pole to pole in vast circulatory systems that moderated temperatures across continents, frozen seas lie silent under ice layers thick enough to bury entire mountain ranges. The familiar blue marble of Earth has become something else, entirely, a pale, reflective world that sends almost all the sun's energy back into the void, creating a feedback loop of cooling so efficient that it becomes self-sustaining across geological epochs. This frozen Earth moves through its orbit with the same gravitational precision it has always known, following elliptical paths that bring it closer to and farther from the sun in cycles that once meant the difference between seasons of growth and dormancy. But its surface tells a story of transformation so radical that it challenges every assumption about planetary habitability and the narrow ranges of temperature and chemistry that allow liquid water to persist. The very mechanisms that once made Earth a dynamic, weather-swept world have now conspired to lock it in a state of crystalline stillness that extends across timescales difficult for the human mind to fully comprehend. Beneath this ice, the planet's molten core continues to churn at temperatures that exceed the melting point of iron, driving magnetic fields that still shield the world from cosmic radiation and solar wind. The dynamo effect that protects the planet's atmosphere operates with the same fundamental physics it always has, even as the surface above lies locked in temperatures that would make the Antarctic seem tropical by comparison. Tectonic plates continue their slow dance along the boundaries where continental masses meet oceanic crust, though their movements remain hidden beneath kilometers of solid water that has accumulated over millions of years of snowfall and compression. Only the patient work of volcanoes hints at the geological processes that continue in the planet's depths, their heat creating brief oases of liquid water around volcanic vents on the seafloor before the surrounding cold reclaims these temporary refugees. These volcanic exhalations release carbon dioxide into an atmosphere already laden with ice crystals, beginning a slow accumulation of greenhouse gases that will, over tens of millions of years, eventually challenge the ice's dominion over the planet's surface temperature. The ice itself becomes a landscape of subtle variation and surprising complexity, ridges and valleys carved by winds that still circle the globe even in this frozen state. Areas where the frozen surface buckles under its own immense weight, like the skin of a cooling custard. Places where the white expanse stretches flat and featureless to every horizon in a demonstration of geometric perfection that would not look out of place on the moons of Jupiter or Saturn. Pressure ridges form where ice sheets collide and overlap, creating mountain ranges of frozen water that rise hundreds of meters above the surrounding plains of white. In this world of perpetual winter, time moves differently than it will during the more familiar epochs of Earth's history. Seasons still exist in name. The planet's axial tilt ensures that some regions receive more direct sunlight than others throughout the year, but the difference between summer and winter becomes academic when both arrive over surfaces that reflect light like perfectly polished mirrors. The longest days of summer bring temperatures that barely rise above the threshold necessary to sublimate surface ice directly into water vapor, while the depths of winter create conditions so severe that even the carbon dioxide in the atmosphere begins to freeze out as dry ice at the polar regions. Scientists studying this ancient freeze through the evidence preserved in rock formations have discovered that it was not merely cold, but systematically, almost mathematically cold, a state maintained by feedback mechanisms so powerful and self-reinforcing that they created what climatologists recognize as a stable alternative climate state. The mechanisms that drove Earth into this condition created feedback loops so powerful that the planet became trapped in its own refrigeration system, like a planetary-scale air conditioner that cannot be turned off. Once enough ice formed to reflect sufficient sunlight back to space, the cooling accelerated in ways that made warming nearly impossible through any mechanism short of massive volcanic outgassing or changes in solar luminosity. It was, in many respects, the most successful climate system Earth has ever produced successful. That is, at maintaining its own frozen equilibrium across time periods that dwarf the entire history of complex life on the planet. The ice age that humans experienced just 20,000 years ago lasted mere tens of thousands of years and covered only portions of the northern continents. This cryogenian freeze persisted for periods measured in the tens of millions of years and covered the entire planet in ice thick enough that no sunlight penetrated to the ocean floor except in the immediate vicinity of volcanic hot springs. Yet even in this state of planetary hibernation, mysteries persist like dreams half remembered upon waking. How did the microscopic life that existed in Earth's oceans before the freeze manage to survive such comprehensive refrigeration? What delicate balance of atmospheric chemistry and volcanic activity eventually allowed enough greenhouse gases to accumulate to challenge the ice's dominion? And perhaps, most intriguingly, how did a planet so thoroughly committed to being frozen, so efficiently designed to maintain its own crystalline state, ever manage to wake up at all? These questions linger in the geological record like fragments of truth scattered across millions of years of sedimentary stone, preserved in the chemical signatures of ancient ice and the fossil remains of organisms that somehow found ways to persist through the longest winter in planetary history. The answers, when they come, will emerge slowly from the patient work of scientists reading the stories written in layers of rock, each stratum a page in Earth's autobiography of transformation and endurance. Before the great stillness descends, Earth drifts through the late Proterozoic eon in a state of relative warmth that will soon seem like a fever dream of abundance. The oceans stretch blue-green beneath skies that have never known the weight of continental ice sheets, their surfaces dimpled by winds that carry moisture across vast expanses of open water. Temperatures hover in ranges that allow liquid water to exist from the deepest abyssal plains to the shallowest coastal shelves, creating a planetary bathtub of remarkable thermal stability. The continents themselves exist in configurations that would be alien to any modern observer, arranged in patterns that reflect the slow dance of plate tectonics across hundreds of millions of years. Rodinia, the supercontinent that dominated this earlier Earth, has begun its slow dissolution along rift valleys that will eventually separate land masses by thousands of kilometers of new oceanic crust. These continental fragments drift across the planet's surface at rates measured in centimeters per year. Their movements imperceptible to any hypothetical observer, but profound in their cumulative effect on global climate patterns and ocean circulation. In the seas that surround these ancient landmasses, life exists in forms so microscopic that millions of individual organisms could fit within a single drop of seawater, yet so numerous that their collective presence colors entire ocean basins with subtle shifts in hue and opacity. Cyanobacteria form vast mats on shallow seafloors, their photosynthetic processes steadily releasing oxygen into an atmosphere that has only recently learned to accommodate this reactive gas in significant concentrations. The Great Oxygenation Event, which transformed Earth's atmosphere from a methane-rich reducing environment to an oxygen-rich oxidizing one, lies several hundred million years in the past, but its effects continue to reverberate through every aspect of planetary chemistry. These bacterial communities exist in a world without predators large enough to significantly impact their populations, creating ecosystems of remarkable stability and predictability. Stromatolites, layered structures built by successive generations of cyanobacteria, grow in shallow waters like living reefs. Their growth rates so slow that individual structures represent archives of environmental conditions spanning thousands of years. Each thin layer preserves chemical signatures of the seawater in which it formed, creating geological documents that will eventually allow future scientists to reconstruct the precise conditions that preceded Earth's descent into global refrigeration. The atmosphere itself hovers in a composition that represents a delicate balance between biological processes and geological ones. Oxygen concentrations remain lower than they will become during later epochs, while carbon dioxide levels fluctuate in response to volcanic activity and the gradual weathering of continental rocks. Methane, produced by primitive organisms called archaea, contributes a significant greenhouse warming effect that helps maintain global temperatures within the narrow range that allows liquid water to persist across most of the planet's surface. Yet, even in this apparently stable world, the mechanisms that will eventually drive Earth toward comprehensive freezing are already beginning to assert themselves with the patience that characterizes all planetary-scale processes. The breakup of Rodinia creates new coastlines where fresh rock surfaces become exposed to chemical weathering by rainfall and ocean spray. These weathering reactions consume carbon dioxide from the atmosphere, converting it into bicarbonate ions that dissolve in seawater and eventually precipitate as carbonate minerals on the sea floor. The process operates so slowly that it would be invisible to any observer watching for mere centuries or millennia. Yet it represents one of Earth's most powerful mechanisms for removing greenhouse gases from the atmosphere over geological timescales. As Rodinia continues to fragment, the total surface area of continental rock exposed to weathering increases, accelerating the rate at which atmospheric carbon dioxide gets locked away in sedimentary deposits that accumulate in ocean basins. Simultaneously, the changing configuration of continents begins to alter the patterns of ocean circulation that have maintained global temperature stability for millions of years. Warm equatorial currents that once carried heat toward higher latitudes find their paths blocked by new continental barriers, while cold polar waters begin to flow into regions that have known only tropical warmth for countless previous epochs. These circulation changes operate with the same inexorable patience as continental drift itself, shifting global heat distribution in ways that will not become apparent for millions of years. The sun that illuminates this pre-glacial world burns with slightly less intensity than it will during later periods of Earth's history, a consequence of stellar evolution processes that gradually increase the fusion rate in the solar core over billions of years. This reduced solar luminosity means that Earth requires higher concentrations of atmospheric greenhouse gases to maintain the same surface temperatures that will later be sustainable with less atmospheric insulation. The planet exists in a state of climate sensitivity where relatively small changes in greenhouse gas concentrations can trigger disproportionately large changes in global temperature. Marine organisms continue their daily routines of photosynthesis and respiration, unaware that their collective metabolic activities are slowly shifting the chemical balance of the ocean atmosphere system. Seasonal blooms of phytoplankton rise and fall in response to changes in light availability and nutrient concentrations, their populations cycling through growth and decay in patterns that have remained essentially unchanged for hundreds of millions of years. In the deeper ocean basins, sediments accumulate grain by grain, preserving a record of environmental conditions that will eventually provide crucial evidence for understanding how Earth transitioned from this warm, stable state to the comprehensive glaciation that awaits. Each layer of sediment represents a snapshot of ocean chemistry, atmospheric composition, and biological productivity, creating an archive that spans the entire transition from greenhouse to icehouse conditions. The iron formations that characterize this period reflect ocean chemistry dominated by dissolved iron compounds that precipitate in response to seasonal changes in oxygen availability. These banded iron formations create some of the most visually striking rock sequences in Earth's geological record, their alternating layers of iron oxides and silica recording the rhythmic cycles of an ocean ecosystem balanced on the edge of a transformation that will reshape the entire planet. Volcanic activity continues at levels that will seem almost quiescent compared to the dramatic outgassing that will eventually be required to rescue Earth from its frozen state. The steady release of carbon dioxide from volcanic sources provides a baseline level of greenhouse warming that helps maintain current climate conditions. Yet this same volcanic contribution proves insufficient to counteract the gradual cooling that begins as weathering rates increase and ocean circulation patterns shift. The stage is set, though no conscious observer could recognize it, for one of the most dramatic climate transitions in planetary history. The mechanisms of global cooling gather strength like a storm system organizing itself across vast distances and timescales, each component process operating within normal parameters, yet combining to create conditions that will transform Earth into something unprecedented in its 4 billion-year history. The first breath of winter arrives not as a sudden chill, but as a subtle shift in the planet's thermal equilibrium, a gradual tilting of the balance between incoming solar radiation and outgoing heat that unfolds across thousands of years with the patience of geological time. High in the northern latitudes, where summer sunlight strikes the Earth's surface at increasingly oblique angles, temperatures begin to hover closer to the freezing point of water during what were once reliably warm seasons. Snow that fell during previous winters lingers longer into spring, creating patches of white that persist through summer months that should have melted them away completely. These surviving snow patches represent more than mere meteorological curiosities. They constitute the nucleation sites for a planetary transformation that will eventually encompass every latitude from pole to pole. Each patch of unmelted snow reflects sunlight back to space with an efficiency that bare ground or vegetation cannot match, creating localized cooling effects that make it even more likely that the following winter's snowfall will survive the subsequent summer's warmth. The process feeds upon itself with the relentless logic of positive feedback, each surviving patch of ice making the survival of additional patches more probable. The atmosphere above these growing ice fields begins to develop circulation patterns that reinforce the cooling trend through mechanisms that operate on scales ranging from local weather systems to planetary-scale atmospheric dynamics. Cold air masses that form over ice-covered surfaces become denser and more stable than the surrounding atmosphere, creating high-pressure systems that deflect storm tracks and reduce the amount of warm, moist air that reaches the regions where ice is accumulating. The ice creates its own weather, and that weather favors the formation of more ice. Continental ice sheets begin to form through the gradual accumulation and compression of snow layers that no longer completely melt during summer months. In regions where annual snowfall exceeds annual melting by even modest amounts, snow accumulates year after year, its lower layers compressed by the weight of subsequent years' accumulation until individual snowflakes transform into granular ice and eventually into the dense, crystalline ice that characterizes major ice sheets. The process requires thousands of years to create ice masses of significant thickness, yet once begun, it proceeds with inevitable momentum towards scales that will eventually dwarf any ice formations in Earth's more recent history. The growing ice sheets exert gravitational effects on the surrounding landscape that become measurable as the ice masses reach thicknesses measured in hundreds of meters. The sheer weight of accumulated ice begins to depress the underlying bedrock, creating bowl-shaped depressions that allow ice to accumulate to even greater depths. These isostatic adjustments of the Earth's crust represent the planet's solid surface responding to the redistribution of mass as water transitions from liquid oceans to solid ice sheets, a process that operates through the same mechanisms that cause continents to rise gradually after the removal of overlying ice masses. Ocean levels begin their slow descent as increasing quantities of water become locked in continental ice sheets, exposing coastal areas that have remained submerged for millions of years. The emerging coastlines reveal landscapes sculpted by previous sea levels, creating new surfaces for weathering and erosion that further accelerate the removal of carbon dioxide from the atmosphere. These newly exposed continental shelves provide vast areas of fresh rock surface where chemical weathering can proceed at enhanced rates, consuming atmospheric greenhouse gases even more rapidly than before. The ocean circulation patterns that have maintained global thermal equilibrium for millions of years begin to respond to the changing distribution of land and sea ice. Warm surface currents that once carried tropical heat toward higher latitudes encounter barriers of floating sea ice that reflect solar radiation and insulate the ocean surface from atmospheric heat exchange. The formation of sea ice creates a positive feedback loop where ice formation makes additional ice formation more likely. As the white surface of sea ice reflects far more sunlight than the dark surface of open ocean water, deep ocean currents driven by temperature and salinity differences begin to strengthen as the temperature gradient between equatorial and polar regions increases. These thermohaline circulation patterns transport cold water from polar regions toward the equator at depths that insulate it from surface warming, creating a global conveyor belt that efficiently distributes cold water throughout the world's ocean basins. The enhanced circulation helps maintain cold temperatures even in regions that receive substantial solar heating, as cold deep water upwells to replace warm surface water that moves poleward. Atmospheric carbon dioxide concentrations continue their gradual decline as weathering processes accelerate and volcanic outgassing proves insufficient to replace the greenhouse gases being removed from the atmosphere. The reduced greenhouse effect allows more of Earth's thermal radiation to escape directly to space, creating a cooling trend that reinforces all the other mechanisms that favor ice formation over ice melting. The atmosphere becomes increasingly transparent to outgoing long-wave radiation while remaining effective at reflecting incoming solar radiation off the growing expanses of ice and snow. The biological communities that have dominated Earth's oceans for hundreds of millions of years begin to experience the first signs of environmental stress as cooling temperatures and changing ocean chemistry challenge the stability of ecosystems that have known remarkable constancy throughout previous epochs. Photosynthetic organisms that require specific temperature ranges for optimal growth find their habitable zones shifting toward lower latitudes, while cold-adapted species begin to expand their ranges into regions that were previously too warm to support their metabolic requirements. Marine productivity begins to fluctuate in response to changing nutrient availability as altered ocean circulation patterns modify the distribution of dissolved minerals and organic compounds that support the base of aquatic food webs. These changes in biological productivity create additional feedback effects on atmospheric composition, as reduced photosynthetic activity means less carbon dioxide is removed from the atmosphere through biological processes, while enhanced decomposition of organic matter in warming equatorial regions releases additional carbon dioxide to the atmosphere. The transition from greenhouse to icehouse conditions accelerates as multiple feedback mechanisms begin to operate simultaneously, each reinforcing the others in ways that make the cooling trend increasingly difficult to reverse through any mechanism short of massive volcanic outgassing or significant changes in solar luminosity. The planet commits itself more deeply to refrigeration with each passing millennium, as the physical and chemical processes that favor ice formation become more dominant relative to those that favor ice melting. What began as subtle changes in seasonal weather patterns has initiated a cascade of atmospheric, oceanic, and biological responses that will ultimately transform Earth into a world where ice extends from pole to pole. The mechanisms of planetary cooling gather momentum like a vast machine whose operation depends on the successful coordination of processes operating at every scale, from local weather systems to global atmospheric circulation, each component contributing to an outcome that no individual process could achieve alone. Ice meets the ocean's edge with the measured deliberation of continental drift itself, advancing centimeter by centimeter across landscapes that have known liquid water for geological ages spanning hundreds of millions of years. The glacial margins creep southward from polar regions with such patience that their movement would be imperceptible to any observer watching for mere centuries. Yet their cumulative advance represents one of the most dramatic geographical transformations in planetary history. Where ice encounters ocean, the meeting creates phenomena that will reshape both the atmosphere above and the seafloor below through processes that operate on scales ranging from molecular to continental. The advancing ice sheets reach coastlines that have remained stable since the breakup of ancient supercontinents, encountering oceanic waters whose temperatures still hover several degrees above the freezing point. The collision between ice and sea creates a boundary zone of remarkable complexity, where glacial ice carves into the ocean as icebergs while simultaneously freezing the surface waters it contacts. These newly formed icebergs drift outward from the continental margins, carrying with them fragments of terrestrial landscapes embedded within ice that formed from snowfall over inland regions thousands of years earlier. as icebergs melt in the warmer oceanic waters beyond the immediate coastal zone. They release fresh water that reduces the salinity of surface seawater and makes it more prone to freezing at higher temperatures than normal oceanic conditions would allow. This dilution effect creates expanding zones around each iceberg, where sea ice can form even when ambient water temperatures remain above the typical freezing point of seawater. The process generates more floating ice, which reflects additional solar radiation and contributes to further cooling of both the atmosphere and the ocean surface. The formation of sea ice proceeds through crystallization processes that exclude salt from the growing ice structure, concentrating brine in the remaining liquid water and making it denser than the surrounding seawater. This dense, salt-enriched water sinks toward the ocean floor, creating convection currents that transport cold water to abyssal depths where it can persist for centuries before returning to the surface through deep ocean circulation patterns. The enhanced production of cold, dense water accelerates the global thermohaline circulation that distributes cooling effects throughout the world's ocean basins. Coastal regions that have supported thriving marine ecosystems for millions of years find themselves transformed into landscapes of ice and grinding glacial activity as continental ice sheets advance directly into oceanic waters. The advancing ice scours the seafloor in shallow coastal areas, removing sediments that have accumulated for geological ages and redistributing them across broader areas of the continental shelf. These glacially transported sediments will eventually provide crucial evidence for future scientists attempting to reconstruct the extent and timing of this ancient glaciation. The boundary between ice and ocean becomes a zone of intense mechanical activity as tidal forces cause floating ice shelves to flex and fracture, creating pressure ridges where ice masses collide and override each other. These ice pressure ridges can reach heights of several dozen meters above sea level, forming temporary mountain ranges of frozen seawater that provide elevated platforms from which additional cooling can radiate across the surrounding landscape. The constant grinding and reformation of sea ice creates acoustic environments dominated by the sounds of ice crystals fracturing and reforming under pressure. Ocean currents that once transported warm tropical waters toward higher latitudes encounter increasing expanses of floating ice that insulate the ocean's surface from atmospheric heat exchange and reflect solar radiation with efficiency approaching that of fresh snow. The currents themselves begin to cool as they flow beneath growing ice covers, their heat content diminished by conductive transfer to the overlying ice and by reduced solar heating of surface waters. These cooled currents carry their reduced thermal energy to regions that have previously relied on oceanic heat transport to maintain temperatures above freezing. The atmospheric circulation patterns above regions where ice meets ocean undergo fundamental reorganization as the temperature contrast between ice-covered surfaces and open water creates strong pressure gradients that drive enhanced wind systems. These winds distribute cold air masses over increasingly large areas, while simultaneously increasing the rate of heat loss from any remaining areas of open water through enhanced evaporation and convective cooling. The winds also transport ice crystals and snow across vast distances, seeding ice formation in regions that might otherwise remain too warm to support spontaneous freezing. Marine organisms that have evolved in oceanic environments, characterized by relatively stable temperatures and salinity levels, find themselves confronting environmental changes that challenge the fundamental assumptions upon which their metabolic processes depend. Species adapted to warm surface waters retreat toward lower latitudes, concentrating in shrinking refugia where oceanic conditions still approximate those that have characterized their evolutionary history. Meanwhile, cold-adapted organisms begin to colonize newly frigid waters. Though their populations remain limited by the reduced biological productivity that characterizes ice-covered oceanic regions, The chemical composition of seawater in coastal zones begins to shift as glacial ice introduces fresh water with different dissolved mineral content than typical oceanic waters. These changes in ocean chemistry affect the solubility of various compounds and alter the pH balance that influences biological processes ranging from shell formation in marine organisms to the rate at which atmospheric carbon dioxide dissolves into seawater. The modifications to ocean chemistry create additional feedback effects that influence both the rate of ice formation and the atmospheric concentration of greenhouse gases. Underwater. The advance of ice into oceanic regions creates new types of seafloor environments as glacial ice grounds on shallow areas of the continental shelf and begins to scour the underlying sediments. These ice contact environments generate unique geological formations that will persist long after the ice retreats, providing evidence of the extent to which continental glaciation extended into oceanic regions. The grounding of ice on the seafloor also creates zones where oceanic circulation becomes restricted, leading to the development of isolated water masses with distinct temperature and chemical characteristics. The progressive cooling of oceanic regions adjacent to ice-covered land masses establishes temperature gradients that drive atmospheric circulation patterns capable of transporting Arctic air masses toward equatorial regions with unprecedented efficiency. These enhanced meridional circulation patterns begin to challenge the thermal equilibrium that has maintained ice-free conditions in tropical regions for hundreds of millions of years. The cooling effects that originated in polar regions begin to propagate toward the equator through both atmospheric and oceanic mechanisms that operate with increasing effectiveness as the total area of ice-covered surface continues to expand. The meeting of ice and ocean thus represents not merely a geographical boundary, but a dynamic interface where multiple Earth system processes interact to accelerate the planetary transition toward comprehensive glaciation. Each mechanism reinforces the others in ways that make the advance of ice increasingly rapid and increasingly difficult to reverse through any natural process short of massive changes in external forcing factors such as solar luminosity or volcanic activity. The albedo engine awakens with the quiet efficiency of a planetary thermostat responding to its own internal logic, transforming Earth's relationship with solar radiation through the simple but profound physics of reflection. Where once dark ocean waters absorbed 90% of the sunlight that reached their surfaces, converting electromagnetic radiation into thermal energy that warmed both water and atmosphere. Now, white ice reflects that same solar energy back towards space, with an efficiency that approaches the theoretical maximum for naturally occurring surfaces. This fundamental shift in how Earth interacts with its primary energy source initiates a cooling cascade that feeds upon itself with mathematical precision. The albedo effect operates through principles so straightforward that they can be demonstrated with a thermometer and two pieces of cloth, one black and one white. Yet when applied at planetary scales, these same principles become capable of transforming entire worlds. Fresh snow reflects between 80 and 90% of incident solar radiation, while open ocean water reflects less than 10%, creating a difference in energy absorption that amounts to roughly 800 watts per square meter of surface area, equivalent to the energy output of 800 small electric heaters concentrated within each square meter of planetary surface. As ice coverage expands from polar regions toward lower latitudes, the total amount of solar energy that Earth absorbs decreases in direct proportion to the area covered by highly reflective ice and snow. This reduced energy absorption leads to lower atmospheric temperatures, which in turn make it easier for additional ice to form and persist through seasons that would previously have melted it away. The process becomes self-perpetuating through feedback mechanisms that operate with the relentless consistency of physical law. each increment of new ice making additional ice formation more probable. The mathematical progression of albedo-driven cooling follows exponential rather than linear patterns, as small increases in ice coverage produce disproportionately large effects on global energy balance. When ice coverage reaches certain threshold percentages of total planetary surface area, the cooling effects begin to accelerate rapidly rather than proceeding at the gradual pace that characterized the initial stages of glaciation. These threshold effects occur because the albedo feedback operates in conjunction with other cooling mechanisms, creating compound effects that exceed the sum of individual cooling processes. Atmospheric circulation patterns respond to the altered energy distribution by developing more pronounced temperature gradients between ice-covered and ice-free regions, driving wind systems that transport cold air masses across increasingly large portions of the planet's surface. These enhanced circulation patterns help distribute the cooling effects of high albedo surfaces far beyond the immediate vicinity of ice-covered areas, allowing the albedo engine to influence global climate through atmospheric teleconnections that operate across continental and oceanic distances. The spectral characteristics of reflected solar radiation from ice-covered surfaces differ significantly from the thermal radiation that Earth emits to space, creating wavelength-dependent effects that influence atmospheric chemistry in ways that extend far beyond simple temperature changes. Solar radiation reflected by ice remains in the visible and near-infrared portions of the electromagnetic spectrum, while thermal radiation from Earth's surface occurs primarily in the far infrared wavelengths that interact more strongly with atmospheric greenhouse gases. The increased reflection of visible light reduces the amount of energy available for conversion to thermal radiation, diminishing the greenhouse effect's ability to trap outgoing heat. Snow and ice surfaces develop complex optical properties that enhance their reflective efficiency through multiple scattering of light within the crystalline structure of frozen water. Individual ice crystals act as microscopic mirrors that redirect incoming photons in random directions, ensuring that most solar radiation undergoes multiple reflection events before either being absorbed or escaping back to space. This internal scattering makes ice surfaces more reflective than would be predicted from the optical properties of solid water alone, contributing additional efficiency to the planetary albedo engine. The aging and metamorphosis of snow and ice surfaces influence their reflective properties in ways that create temporal variations in albedo effectiveness. Fresh snowfall exhibits maximum reflectivity, while older snow that has undergone cycles of partial melting and refreezing develops lower albedo values due to changes in crystal structure and the incorporation of atmospheric dust and debris. However, even aged ice surfaces maintain albedo values far higher than any non-frozen surface, ensuring that the cooling effects persist even as individual ice masses undergo seasonal or multi-annual cycles of formation and modification. Cloud formation patterns over ice-covered regions contribute additional albedo effects through increased reflection of solar radiation by water droplets and ice crystals suspended in the atmosphere. The temperature and humidity conditions that prevail over extensive ice sheets favor the formation of low-altitude clouds that enhance the total reflectivity of the Earth atmosphere system beyond what would be achieved by surface ice alone. These cloud albedo interactions create secondary feedback mechanisms that amplify the primary albedo effects of surface ice coverage. Regional variations in solar angle and seasonal illumination patterns interact with surface albedo to create geographic differences in the effectiveness of ice albedo feedback mechanisms. Polar regions, where the sun remains low on the horizon even during summer months, experience less dramatic albedo effects than would occur if the same ice coverage existed at lower latitudes where solar radiation strikes the surface at higher angles. As ice coverage expands toward equatorial regions, the albedo engine becomes increasingly effective at reducing global energy absorption because each additional unit of ice coverage occurs in regions where solar radiation is more intense. The persistence of high albedo surfaces through multiple seasonal cycles allows the albedo engine to operate continuously rather than only during winter months when ice coverage reaches its maximum extent. Ice that survives through summer seasons maintains its reflective properties throughout the year, providing consistent cooling effects that prevent the seasonal recovery of temperatures that might otherwise melt additional ice during subsequent winters. This year-round operation of the albedo feedback mechanism contributes to the stability of the glaciated state once it becomes established. Ocean ice coverage develops its own albedo dynamics as sea ice thickness, and coverage respond to both atmospheric cooling and oceanic heat transport. Thin sea ice exhibits lower albedo values than thick ice due to partial transparency that allows some solar radiation to reach the underlying dark ocean water, while thick sea ice approaches the reflectivity of terrestrial ice sheets. The transition from thin to thick sea ice represents a crucial threshold in the development of oceanic albedo feedback, as thick ice becomes essentially opaque to solar radiation and maximizes the reflection of incident energy. The albedo engine operates with particular effectiveness during summer months when solar radiation reaches its peak intensity, precisely the time when ice surfaces face their greatest threat from melting. This temporal alignment between maximum solar input and maximum albedo feedback creates a defense mechanism that becomes more effective as the threat to ice persistence increases. The system exhibits an almost biological-like responsiveness to external stresses, automatically generating stronger cooling effects when warming pressures intensify. As global ice coverage approaches the critical thresholds that will eventually lead to ice extending across equatorial regions, the albedo engine evolves from a regional climate modifier into a planetary-scale climate controller capable of maintaining stable ice coverage across all latitudes. The mathematical inevitability of albedo feedback ensures that once certain coverage thresholds are exceeded, the maintenance of global glaciation becomes energetically favored over any ice-free alternative climate state. Continents beneath crystal sheets disappear into landscapes that transform the very meaning of geography, where familiar concepts of mountain and valley, coastline and interior become abstractions buried beneath ice masses whose thickness exceeds the height of many mountain ranges that will one day rise from these same locations. The ice sheets that advance across continental surfaces operate on scales that dwarf any subsequent glaciation in Earth's history, accumulating to depths measured in multiple kilometers rather than the hundreds of meters that characterize even the most extensive ice ages of more recent geological periods. These continental ice sheets develop through processes that require thousands of years to reach their full thickness, yet once established, they create landscapes so thoroughly transformed that the underlying bedrock topography becomes completely irrelevant to surface geography. River valleys that carve their paths through continental surfaces over millions of years vanish beneath uniform expanses of ice, their complex networks of tributaries and watersheds reduced to subtle variations in the thickness of overlying frozen water. Mountain ranges that once defined continental drainage patterns and influenced regional climate systems become buried beneath ice sheets, whose surfaces rise higher than the peaks they cover. The weight of accumulated ice reaches magnitudes that exceed the load-bearing capacity of the Earth's crust, initiating isostatic adjustments that depress continental surfaces by hundreds of meters below their original elevations. This crustal subsidence operates through the same mechanisms that allow icebergs to float in water, as the relatively low density of ice displaces the higher density rock of the continental crust downward into the underlying mantle. The depression of continental surfaces beneath ice loads creates basin-like configurations that allow even greater accumulations of ice than would be possible on rigid, non-deforming surfaces. Beneath the ice, the solid Earth continues its geological processes with the same fundamental mechanisms that have operated throughout planetary history. Though the presence of multi-kilometer ice sheets modifies these processes in ways that create unique conditions found nowhere else in Earth's geological record. The immense pressure exerted by overlying ice creates temperature and pressure conditions at the ice-bedrock interface that approach those found in metamorphic environments, leading to the formation of pressure-melted water films that lubricate the contact between ice and rock. These basal water films allow continental ice sheets to flow like extremely viscous fluids, despite their solid crystalline structure, creating internal circulation patterns that transport ice from regions of accumulation toward margins where the ice either calves into the ocean or melts during brief seasonal warming periods. The flow of ice within continental ice sheets operates through crystal deformation mechanisms that reshape individual ice crystals under pressure, allowing the ice mass to deform and move despite temperatures well below the normal melting point of water. The thermal regime within continental ice sheets creates temperature gradients that influence both the flow characteristics of the ice and the preservation of environmental records contained within the frozen water. Surface temperatures that may reach several tens of degrees below freezing create steep temperature gradients that extend downward through the ice mass, with temperatures approaching the pressure melting point at the base of the thickest accumulations. These internal temperature gradients drive convective circulation within the ice that influences both the rate of ice flow and the distribution of atmospheric gases and debris incorporated during ice formation. Annual accumulation layers within the ice sheets preserve detailed records of atmospheric conditions during each year of ice formation, creating archives of environmental information that span the entire duration of continental glaciation. These layers contain atmospheric gases, volcanic ash, cosmic dust, and other atmospheric constituents that provide snapshots of global environmental conditions with temporal resolution measured in individual years. The preservation of these environmental records requires the specific temperature and pressure conditions that exist only within thick continental ice sheets. The margins of continental ice sheets create unique geological environments where the immense pressure of overlying ice encounters the ambient pressure of the surrounding atmosphere or ocean. These marginal zones experience intense mechanical stress that fragments bedrock and creates distinctive landforms through processes that operate only in the presence of continental-scale ice loads. The grinding action of ice flowing over bedrock surfaces polishes and sculpts the underlying rock, creating streamlined landforms that record the direction and magnitude of ice flow long after the ice itself has disappeared. Subglacial drainage systems develop beneath continental ice sheets as pressure-melted water at the ice-bedrock interface flows along hydraulic gradients that may differ significantly from the surface topography of either the bedrock or the overlying ice. These subglacial water systems transport dissolved minerals and rock fragments across continental distances, creating chemical and sedimentary signatures that provide evidence of processes operating in environments completely isolated from atmospheric or oceanic influences. The atmospheric conditions above continental ice sheets develop characteristics that influence weather patterns across much larger areas than the ice sheets themselves occupy. The thermal properties of ice surfaces create persistent high-pressure systems that deflect storm tracks and modify precipitation patterns across entire continents. These atmospheric effects extend the climatic influence of continental ice sheets far beyond their physical boundaries, contributing to the maintenance of cold, dry conditions in regions that remain ice-free. Wind patterns over continental ice sheets develop katabatic flow systems, where cold, dense air formed over ice surfaces flows downward along the ice surface gradients toward lower elevations. These gravity-driven wind systems can reach velocities that exceed those of most storm systems, creating scoured landscapes along ice margins and transporting ice crystals and snow across vast distances from their source regions. The persistence of katabatic winds contributes to the maintenance of cold conditions in areas adjacent to ice sheets and helps prevent seasonal warming that might otherwise lead to ice margin retreat. The reflective properties of continental ice sheets influence not only local and regional climate conditions, but also the planetary energy balance in ways that affect global atmospheric circulation patterns. The high albedo of ice-covered continents reduces the amount of solar energy absorbed at these latitudes, creating enhanced temperature gradients between ice-covered and ice-free regions that drive more vigorous atmospheric circulation patterns. These enhanced circulation systems transport cold air masses from ice-covered regions toward lower latitudes with increased efficiency. Biological processes beneath continental ice sheets operate in environments characterized by constant darkness, temperatures near freezing, and isolation from atmospheric influences that might otherwise provide energy sources for metabolic activities. The few organisms capable of surviving in these subglacial environments depend on chemical energy sources derived from rock weathering or geothermal processes rather than photosynthesis, creating ecosystems that operate according to fundamentally different principles than surface biological communities. The long-term stability of continental ice sheets depends on the balance between accumulation rates at high elevations and ablation rates at margins, a balance that becomes increasingly favorable to ice maintenance as global temperatures continue to decline. The feedback mechanisms that initially drove ice sheet formation continue to operate throughout the period of maximum glaciation, ensuring that continental ice sheets remain stable even as they modify their own environmental conditions through their effects on atmospheric and oceanic circulation patterns. The transformation of entire continents into ice-covered landscapes represents one of the most complete reorganizations of Earth's surface geography in planetary history, creating conditions that will persist for tens of millions of years before volcanic processes generate sufficient atmospheric warming to challenge the stability of these massive ice accumulations. The silent seas surrender with a resignation that speaks to the mathematical inevitability of planetary-scale cooling. As even the equatorial oceans that have maintained liquid water through hundreds of millions of years of climatic variation begin to succumb to the advancing ice that has already claimed higher latitudes. This represents the culmination of a cooling process that transforms Earth from a world where ice exists only at the poles into a planet where frozen water extends across every latitude from the Arctic to the Antarctic, covering oceanic regions that have served as thermal reservoirs, stabilizing global climate since the formation of the first permanent seas. The freezing of equatorial oceans proceeds through mechanisms that differ fundamentally from the ice formation processes that characterized higher latitudes, as tropical seas must overcome not only their higher baseline temperatures, but also the continuous input of solar energy that reaches maximum intensity in these regions. The conquest of equatorial waters by ice requires the convergence of multiple cooling mechanisms operating simultaneously, each contributing to a cumulative effect that overwhelms the thermal capacity of oceanic water masses that contain energy equivalent to millions of years of solar heating. Sea ice formation in tropical regions begins at the surface, where radiative cooling to space can operate most efficiently, creating thin films of ice that initially form only during the coldest portions of diurnal temperature cycles. These fragile ice layers break apart and reform repeatedly as wind and wave action prevent the establishment of continuous ice coverage. Yet each cycle of formation and destruction contributes to the cooling of surface waters and increases the probability that subsequent ice formation will achieve greater stability and persistence. The thermal inertia of tropical oceans creates resistance to freezing that requires sustained cooling over periods measured in millennia rather than the seasonal timescales that proved sufficient for ice formation at higher latitudes. Ocean water contains approximately 4,000 times more heat capacity per unit volume than air, meaning that cooling oceanic water masses to freezing temperatures requires the removal of enormous quantities of thermal energy through processes that operate slowly even by geological standards. The patience required for oceanic freezing exemplifies the timescales on which planetary climate transitions actually occur. As surface ice coverage becomes established in tropical regions, it creates insulation barriers that prevent oceanic heat stored in deeper water layers from reaching the surface where it might contribute to ice melting. The formation of even thin ice layers reduces heat transfer between ocean and atmosphere by orders of magnitude compared to open water surfaces, allowing surface cooling to proceed more rapidly while deeper oceanic heat remains trapped beneath the growing ice cover. This insulation effect accelerates the thickening of surface ice once initial ice formation becomes established. The freezing process releases latent heat that temporarily slows the cooling of oceanic water, as the phase transition from liquid to solid water liberates approximately 80 calories of thermal energy for each gram of water that freezes. This latent heat release represents a significant energy source that must be dissipated to space before ice formation can proceed, creating temporary plateaus in the cooling process, where surface temperatures remain constant despite continued heat loss to the atmosphere. The eventual dissipation of this latent heat allows ice thickness to increase through continued freezing of underlying water layers. Ocean circulation patterns that once transported warm water from equatorial regions toward higher latitudes become progressively restricted as surface ice coverage reduces the efficiency of wind-driven surface currents and blocks the exchange of heat between ocean and atmosphere that drives thermohaline circulation. The reduction in oceanic heat transport accelerates the cooling of polar regions, while simultaneously allowing equatorial regions to cool through reduced import of cold water from higher latitudes. The ocean system gradually transitions from a heat redistribution mechanism to a heat storage system isolated beneath ice coverage. The salinity of seawater influences the freezing process in ways that create complex patterns of ice formation and brine rejection, as salt exclusion during ice crystal formation increases the density of remaining liquid water and causes it to sink toward greater depths. This convective mixing distributes the cooling effects throughout the water column more rapidly than would occur through conductive heat transfer alone, accelerating the overall freezing process while creating layered water masses with distinct temperature and salinity characteristics beneath the growing ice cover. Marine ecosystems that have adapted to tropical oceanic conditions over hundreds of millions of years face environmental changes that exceed the tolerance ranges of most organism groups, leading to mass extinctions that eliminate biological communities specialized for warm water environments. The few surviving organisms retreat to refugia around hydrothermal vents or other localized sources of heat that maintain liquid water in small volumes surrounded by vast expanses of frozen ocean. These biological refugia become isolated islands of life in an otherwise sterile frozen seascape. The acoustic environment of freezing oceans transforms as ice formation eliminates the sound transmission pathways that characterize liquid water environments while simultaneously generating new sources of acoustic energy through the mechanical processes of ice crystal formation and structural adjustment under pressure. The cracking and grinding of ice masses create sound patterns that propagate through both the ice and underlying water, establishing acoustic signatures that differ completely from any previous oceanic environment. Atmospheric circulation patterns above freezing equatorial oceans undergo fundamental reorganization as the thermal contrast that once drove tropical atmospheric convection disappears beneath uniform ice coverage. The atmospheric heat engine that creates trade wind systems and seasonal monsoon patterns loses its primary energy source as ice-covered oceans cease to provide the evaporative moisture and thermal energy that drive tropical weather systems. Global atmospheric circulation transitions toward patterns dominated by temperature gradients between ice-covered and remaining ice-free surfaces. The chemical composition of seawater beneath tropical ice undergoes modifications, as reduced biological activity eliminates most of the organic processes that cycle nutrients and maintain oceanic chemical equilibrium. The isolation of oceanic water masses beneath ice coverage allows dissolved compounds to reach concentrations that would not be stable under normal oceanic conditions, creating unique chemical environments that will persist throughout the duration of global glaciation. Tidal forces continue to operate beneath ice-covered oceans, creating flexural stresses in the overlying ice that generate crack systems and pressure ridges through which limited exchange between ocean and atmosphere can occur. These tidal effects become more pronounced as ice thickness increases, creating dynamic ice environments that undergo constant mechanical adjustment despite the apparent static nature of frozen oceanic surfaces. The completion of equatorial ocean freezing marks the achievement of maximum planetary glaciation, a state where Earth's surface approaches the maximum possible albedo and minimum possible heat absorption compatible with its orbital characteristics and solar energy input. This represents the culmination of all the cooling mechanisms that began with subtle changes in continental ice coverage millions of years earlier, demonstrating the cumulative power of feedback systems operating across geological timescales. The silent seas thus represent not merely frozen water, but the transformation of Earth's primary heat transport and storage system into a planetary-scale refrigeration mechanism that will maintain global ice coverage through mechanisms that operate independently of the external factors that initiated the cooling process. Life in frozen refuge persists through strategies of microscopic tenacity that transform the very definition of what constitutes a habitable environment. As organisms that once thrived in the sun-warmed surface, waters of ancient seas adapt to conditions that resemble those found in the most extreme environments of other planetary bodies within the solar system. The comprehensive freezing of Earth's oceans creates a world where liquid water exists only in thin films beneath ice sheets, in geothermal oases around volcanic vents, and in microscopic pockets within ice crystals themselves, reducing the planet's habitable volume to a fraction of its previous extent, while simultaneously creating new ecological niches that operate according to fundamentally different principles than any previous biological systems. Beneath the kilometers-thick ice that covers the global ocean, microscopic communities establish themselves in the narrow interface between frozen surface and liquid depths, existing in boundary environments where temperatures hover within fractions of a degree of the freezing point and where the slightest change in pressure or chemical composition can eliminate their precarious foothold on existence. These interfacial communities depend on the subtle heat flux from deeper ocean layers and the chemical gradients that develop where ice meets liquid water, creating ecosystems that exist in spaces measured in millimeters, yet support biological diversity comparable to much larger environments. The organisms that survive in these frozen refugia represent evolutionary lineages that demonstrate remarkable physiological flexibility, having developed cellular mechanisms that allow them to function at temperatures that approach the theoretical limits for biochemical processes. Their metabolic pathways operate at rates so slow that individual cellular divisions may require months or years to complete. Yet these organisms maintain the essential biological functions that define life through chemical processes that proceed with the patience of geological time. They exist in a state of biological suspended animation that nevertheless preserves the potential for more rapid growth should environmental conditions ever become more favorable. Volcanic hot springs on the seafloor provide islands of thermal energy in the frozen ocean, creating oases where liquid water temperatures may reach several degrees above freezing and where chemosynthetic bacteria can derive energy from the sulfur compounds and dissolved minerals that characterize hydrothermal environments. These geothermal refugia support biological communities that operate independently of solar energy, deriving their metabolic requirements from chemical processes that tap into the planet's internal heat rather than the photosynthetic pathways that characterize surface ecosystems. Around these hydrothermal vents, complex ecological relationships develop as chemosynthetic bacteria provide the primary productivity that supports higher levels of biological organization, including primitive multicellular organisms that filter nutrients from the water and scavenger species that consume organic matter produced by the primary chemosynthetic communities. These vent ecosystems exist as isolated biological islands surrounded by vast expanses of frozen ocean, yet they maintain ecological complexity that rivals much larger biological systems operating under more favorable environmental conditions. The water films that exist at the interface between ice and underlying bedrock create unique habitable environments where microorganisms can access both the mineral nutrients released by rock weathering and the minimal liquid water necessary for biological processes. These subglacial communities exist in permanent darkness, yet maintain metabolic activity through chemical processes that derive energy from the oxidation of minerals and dissolved organic compounds. They represent biological systems that operate at the absolute minimum energy levels compatible with life, demonstrating the remarkable efficiency with which biological processes can extract usable energy from marginal environments. Within the ice itself, microscopic pockets of liquid water persist in spaces between ice crystals where the concentration of dissolved salts and organic compounds depresses the freezing point below that of pure water. These brine inclusions provide habitat volumes measured in cubic micrometers, yet support microbial communities that maintain genetic diversity through horizontal gene transfer and other mechanisms that allow rapid adaptation to changing chemical conditions within their microscopic environments. The reduced biological productivity that characterizes frozen refugia creates ecosystems where nutrient cycling operates at extremely slow rates compared to surface biological systems, with individual atoms of essential elements like nitrogen and phosphorus remaining within biological systems for periods measured in geological timescales, rather than the seasonal or annual cycles that characterize more productive environments. This biological hoarding of nutrients creates communities where every molecule represents a precious resource that cannot be wasted through inefficient metabolic processes. Dormancy strategies become essential survival mechanisms as organisms develop the ability to suspend metabolic activity entirely during periods when environmental conditions fall below the minimum thresholds necessary for active biological processes, then resume normal cellular functions when conditions improve sufficiently to support metabolism. These dormancy capabilities allow biological communities to persist through environmental fluctuations that would otherwise eliminate any organisms dependent on continuous metabolic activity. The genetic diversity preserved within frozen refugia represents a biological archive that maintains the evolutionary potential for more complex life forms despite the severe environmental constraints that limit immediate biological expression of this genetic information. The organisms surviving in these refugia carry within their genetic material the hereditary information that will eventually give rise to the multicellular life forms that dominate more favorable periods in Earth's history, demonstrating the remarkable capacity of biological systems to preserve evolutionary potential through periods of environmental stress. Horizontal gene transfer becomes an increasingly important mechanism for maintaining genetic diversity within small, isolated populations of microorganisms, as the exchange of genetic material between individuals allows rapid adaptation to changing environmental conditions without requiring the large population sizes that would normally be necessary for evolutionary adaptation through sexual reproduction and natural selection. These genetic exchange mechanisms operate with particular efficiency in the high-density microbial communities that characterize biological refugia. The chemical signatures produced by biological processes in frozen refugia create distinctive geochemical environments that will eventually provide evidence for the persistence of life throughout the global glaciation period. As the metabolic byproducts of chemosynthetic and other biological processes create isotopic ratios and chemical concentrations that differ from those produced by purely geological processes. These biological signatures become incorporated into sedimentary deposits that will preserve evidence of life's persistence through Earth's most challenging environmental period. Energy conservation becomes the dominant evolutionary pressure in frozen refugia, favoring organisms that can maintain essential biological functions while minimizing energy expenditure through streamlined metabolic pathways that eliminate any cellular processes not absolutely essential for survival and reproduction. These efficiency adaptations create organisms that represent the ultimate expression of biological minimalism, maintaining life through the most economical possible use of available energy resources. The spatial isolation of biological refugia creates conditions where evolution proceeds independently in each isolated community, leading to the development of endemic species that exist nowhere else on the planet and that represent unique evolutionary experiments in adaptation to extreme environmental conditions. These isolated evolutionary laboratories generate biological diversity through adaptive radiation within extremely constrained environmental niches. Volcanic breath through ice operates with the inexorable persistence of planetary geology as Earth's molten interior continues its 4 billion-year cycle of heat generation and gas release, regardless of the frozen conditions that have transformed the planet's surface into a crystalline shell. Deep beneath the ice sheets that cover continents and oceans, volcanic processes proceed according to the same fundamental mechanisms that have operated throughout geological time, yet their effects on surface conditions undergo profound modification as the gases they release encounter a planetary environment unlike any that has existed during previous epochs of volcanic activity. The volcanic vents that penetrate through kilometers of overlying ice create vertical pathways that connect Earth's molten interior directly to the frozen surface, establishing conduits through which carbon dioxide, water vapor, sulfur compounds, and other volcanic gases can reach the atmosphere despite the comprehensive ice coverage that insulates most of the planet's surface from direct contact with the underlying bedrock. These volcanic chimneys represent the only significant sources of atmospheric input during the frozen epoch, making them crucial components in the planetary chemical cycles that will eventually determine how long the glaciation persists. Carbon dioxide released by volcanic processes accumulates in the atmosphere at rates that depend on the global level of volcanic activity, which varies over geological timescales in response to tectonic processes operating deep within the Earth's interior. During periods of enhanced volcanic activity, carbon dioxide emissions may increase sufficiently to begin measurable warming of the atmosphere, while during periods of reduced volcanism, atmospheric carbon dioxide concentrations may decline through various removal mechanisms that continue to operate despite the frozen surface conditions. The interaction between volcanic gases and ice-covered surfaces creates unique chemical environments where hot volcanic emissions encounter frozen water at temperatures far below the normal boiling point of volcanic fluids. These encounters generate explosive steam production as volcanic heat vaporizes ice, creating localized atmospheric disturbances that can influence weather patterns across continental distances. The steam produced by volcano-ice interactions adds water vapor to an atmosphere that has become extremely dry due to the comprehensive freezing of surface water sources. Subglacial volcanic eruptions create temporary lakes of liquid water beneath ice sheets as volcanic heat melts overlying ice faster than the surrounding cold can refreeze the newly created water. These subglacial lakes provide transient refugia where biological communities can temporarily expand their populations and geographic ranges before cooling temperatures and renewed ice formation force them back into more marginal habitats. The cyclical formation and freezing of subglacial volcanic lakes creates episodic opportunities for biological dispersal across otherwise impassable frozen landscapes. The chemical composition of volcanic gases during the frozen epoch differs from that released during ice-free periods due to the different pressures and temperatures that characterize volcanic processes operating beneath thick ice sheets. The increased pressure exerted by overlying ice affects the solubility of various gases in molten rock, leading to modifications in the proportions of different volcanic emissions and potentially altering the atmospheric effects of volcanic activity compared to similar eruptions occurring under ice-free conditions. Volcanic ash and aerosols released into the atmosphere during eruptions that penetrate through ice coverage create atmospheric disturbances that can influence global climate patterns through their effects on solar radiation transmission and atmospheric chemistry. Volcanic aerosols can either enhance cooling by reflecting additional solar radiation back to space or contribute to warming by absorbing outgoing thermal radiation, depending on their chemical composition and the altitude at which they become distributed within the atmosphere. The thermal energy released by volcanic processes creates localized warming effects that extend far beyond the immediate vicinity of volcanic vents, as heat conduction through ice and rock can maintain above freezing temperatures across areas measured in square kilometers around major volcanic centers. These geothermally heated regions provide expanded habitat areas where biological communities can maintain larger populations and greater genetic diversity than would be possible in the minimal refugia that characterize most ice-covered environments. Volcanic sulfur emissions interact with atmospheric water vapor to create sulfuric acid aerosols that influence both atmospheric chemistry and the radiative properties of the atmosphere in ways that can either enhance or counteract the greenhouse warming effects of volcanic carbon dioxide emissions. The relative importance of sulfur versus carbon dioxide emissions from volcanic sources determines whether individual volcanic events contribute to atmospheric warming or cooling, creating complex feedback relationships between volcanic activity and global climate conditions. The timing and magnitude of volcanic events during the frozen epoch become crucial factors in determining the duration of global glaciation, as volcanic carbon dioxide emissions represent the primary mechanism through which atmospheric greenhouse gas concentrations can increase sufficiently to challenge the stability of global ice coverage. Only sustained periods of enhanced volcanic activity lasting millions of years can generate atmospheric carbon dioxide concentrations high enough to overcome the powerful cooling effects of planetary albedo feedback mechanisms. Hot springs created by volcanic heating of groundwater provide localized sources of liquid water at temperatures that may remain above freezing throughout the year, creating oases of biological activity where organisms can maintain metabolic rates approaching those that characterize more favorable environmental conditions. These geothermal hot springs become centers of biological diversity and activity that serve as sources for recolonization of surrounding areas if environmental conditions ever become more favorable for biological expansion. The interaction between volcanic heat sources and surrounding ice creates convection systems that transport heat upward through ice masses, creating zones of structural weakness where ice may fracture or undergo accelerated melting. These thermally modified ice structures create pathways for enhanced atmospheric exchange and provide access routes through which organisms from subglacial environments can potentially reach surface or near-surface habitats during periods of volcanic activity. Volcanic islands that protrude through oceanic ice coverage provide ice-free land surfaces where atmospheric and geological processes can operate without the insulating effects of ice coverage, creating environmental conditions that approximate those of ice-free planetary surfaces. These volcanic islands become natural laboratories where the transition from ice-covered to ice-free conditions can be observed and where biological communities can experiment with adaptation to non-frozen environments. The cumulative effects of volcanic emissions over millions of years gradually modify atmospheric composition in ways that begin to challenge the chemical equilibrium that maintains frozen surface conditions. As carbon dioxide concentrations slowly approach levels where greenhouse warming can compete with albedo cooling, this gradual atmospheric modification represents the beginning of the physical and chemical processes that will eventually terminate the global glaciation and restore liquid water to planetary surfaces. The persistence of volcanic activity throughout the frozen epoch demonstrates the independence of Earth's internal geological processes from surface climate conditions, ensuring that the planet retains the capacity to modify its own atmospheric composition and eventually escape from even the most stable frozen climate states through the patient accumulation of volcanic greenhouse gases over geological timescales. The greenhouse builds beneath an atmosphere that has become inadvertently patient, as carbon dioxide molecules released by volcanic processes accumulate in concentrations that increase by mere parts per million each year, yet persist for thousands of years once released, creating a slow but inexorable shift in atmospheric composition that operates according to timescales that dwarf human comprehension. This accumulation proceeds without any immediate visible effect on surface conditions, as the powerful albedo feedback mechanisms that maintain global ice coverage continue to reflect solar radiation with undiminished efficiency. Yet the chemical foundation for eventual planetary warming grows stronger with each volcanic exhalation that penetrates the ice-covered surface. The mathematical relationship between atmospheric carbon dioxide concentration and global temperature operates according to logarithmic rather than linear scaling, meaning that each doubling of atmospheric carbon dioxide produces approximately the same increment of global warming regardless of the initial concentration. This logarithmic response creates a situation where the early stages of carbon dioxide accumulation produce minimal temperature effects, while later stages of accumulation can generate dramatic warming once critical threshold concentrations are exceeded. The frozen planet approaches these thresholds with geological patience, building toward climatic transformation through incremental atmospheric changes that remain invisible for millions of years. Atmospheric residence times for carbon dioxide, released during the frozen epoch, extend far beyond those that characterize ice-free periods due to the virtual elimination of biological and oceanic processes that normally remove carbon dioxide from the atmosphere through photosynthesis and dissolution in seawater. The comprehensive freezing of Earth's oceans eliminates the largest carbon dioxide reservoir on the planet, preventing atmospheric carbon dioxide from dissolving into oceanic water and forcing it to remain in gaseous form where it can contribute to greenhouse warming effects. The chemical weathering processes that normally consume atmospheric carbon dioxide through reactions with exposed rock surfaces operate at extremely reduced rates beneath ice-covered continents. As the isolation of bedrock beneath ice sheets prevents most atmospheric carbon dioxide from contacting the mineral surfaces where weathering reactions occur. This reduction in carbon dioxide consumption allows atmospheric concentrations to increase more rapidly than would be possible under ice-free conditions, accelerating the buildup of greenhouse gases that will eventually challenge the stability of global glaciation. Atmospheric circulation patterns distribute volcanic carbon dioxide throughout the global atmosphere with efficiency that ensures relatively uniform concentrations across all latitudes, preventing the formation of regional concentration gradients that might allow carbon dioxide to be removed from the atmosphere through localized processes. The well-mixed nature of atmospheric carbon dioxide ensures that greenhouse warming effects will operate globally rather than only in the vicinity of volcanic sources, creating planetary-scale heating that can eventually overcome regional cooling effects. The infrared absorption characteristics of carbon dioxide become increasingly important as atmospheric concentrations approach levels where greenhouse effects can compete with albedo cooling. As carbon dioxide molecules absorb outgoing thermal radiation from Earth's surface and re-emit it in all directions, including back toward the surface where it contributes additional heating. This radiative forcing operates most effectively in the atmospheric wavelength bands, where ice and snow surfaces emit thermal radiation, creating efficient coupling between surface thermal emission and atmospheric absorption. Water vapor released by volcanic processes contributes additional greenhouse effects as it becomes distributed throughout the atmosphere, yet its atmospheric residence time remains much shorter than that of carbon dioxide due to condensation and precipitation processes that continue to operate despite sub-freezing surface temperatures. The interaction between water vapor and carbon dioxide creates amplifying effects where increased atmospheric carbon dioxide leads to slightly higher temperatures, which increase the atmosphere's capacity to hold water vapor, which in turn contributes additional greenhouse warming through water vapor's strong infrared absorption characteristics. The thermal structure of the atmosphere begins to respond to increasing greenhouse gas concentrations through subtle modifications in temperature profiles that initially affect only the upper atmospheric layers where greenhouse heating operates most efficiently. These upper atmosphere temperature changes influence atmospheric circulation patterns in ways that can modify the distribution of heat between different latitudes and altitudes, potentially creating feedback effects that either enhance or diminish the surface warming effects of increased greenhouse gas concentrations. Stratospheric heating caused by increased greenhouse gas absorption creates temperature inversions that influence the vertical transport of heat and moisture within the atmosphere, potentially affecting cloud formation patterns and atmospheric dynamics in ways that modify the efficiency of heat transport from equatorial to polar regions. These high-altitude atmospheric changes represent the first detectable responses to increasing greenhouse gas concentrations, preceding surface temperature changes by thousands of years. The radiative equilibrium that determines Earth's surface temperature begins to shift as atmospheric greenhouse gas concentrations approach levels where infrared absorption can capture sufficient outgoing thermal radiation to overcome the cooling effects of increased solar reflection by ice-covered surfaces. This shift in radiative balance operates through the same physical principles that govern planetary temperatures around all stars, demonstrating the universal nature of greenhouse effects in planetary atmospheres containing infrared-absorbing gases, feedback mechanisms that will eventually accelerate the transition from ice-covered to ice-free conditions remain dormant during the early stages of greenhouse gas accumulation, as surface temperatures remain too cold to initiate the ice-melting processes that would reduce planetary albedo and create positive feedback effects. The atmosphere continues to build greenhouse warming potential while surface conditions remain locked in their frozen state, creating a situation analogous to a dam holding back water that gradually rises behind it. The concentration thresholds at which atmospheric greenhouse warming can overcome ice albedo cooling represent critical points in planetary climate evolution, beyond which the transition from ice-covered to ice-free states becomes inevitable through positive feedback mechanisms that operate faster than the geological processes that created the initial glaciation. These threshold effects create the potential for rapid climate transitions despite the slow pace of atmospheric change that characterizes the greenhouse gas accumulation phase. Regional variations in volcanic activity create spatial differences in the rate of atmospheric greenhouse gas input. Yet atmospheric mixing processes ensure that these regional differences become smoothed out over time scales much shorter than those required for significant climate change. Maintaining the globally uniform atmospheric conditions necessary for planetary-scale greenhouse effects, the atmosphere operates as an efficient averaging mechanism that converts localized volcanic inputs into global atmospheric modifications. The increasing concentration of atmospheric greenhouse gases creates conditions where even small additional inputs of carbon dioxide or water vapor can produce disproportionately large climate effects. As the atmosphere approaches nonlinear response thresholds, where gradual changes in forcing can trigger rapid changes in climate state, this approach toward threshold conditions creates the potential for sudden climate transitions that will eventually terminate the global glaciation through mechanisms that operate much faster than the geological processes that created it. First cracks in forever appear not as dramatic ruptures, but as hairline fractures in the ice that has defined planetary geography for tens of millions of years. Subtle signs that the mathematical balance between incoming solar energy and outgoing thermal radiation has begun to tip toward the side of warming as atmospheric greenhouse gas concentrations finally approach the critical thresholds, where molecular absorption of infrared radiation can compete with the relentless efficiency of ice albedo cooling. These initial breaks in the ice represent the first visible manifestation of atmospheric changes that have been accumulating for geological ages. Yet their appearance marks the beginning of a transition that will proceed with accelerating momentum once the positive feedback mechanisms of deglaciation begin to operate. The physics of ice failure operates through stress concentration mechanisms that cause small initial cracks to propagate through ice masses with exponential acceleration once critical stress thresholds are exceeded. Transforming microscopic flaws into continental-scale fracture systems through the same mechanical principles that govern the failure of all crystalline materials under load. The thermal stresses created by greenhouse warming generate the initial microscopic fractures that serve as nucleation sites for much larger failures. As differential expansion between warming surface layers and still frozen deeper ice creates internal tensions that exceed the tensile strength of solid water. Along the margins of continental ice sheets, where ice thickness reaches its minimum values and thermal stresses achieve maximum concentration. The first significant ice failures create narrow channels of open water that expose dark ocean surfaces to direct solar heating for the first time in millions of years. These marginal openings absorb solar radiation with efficiencies that exceed 90%, converting electromagnetic energy into thermal energy that immediately begins to warm surrounding ice and accelerate further melting through conductive heat transfer mechanisms that operate much faster than the radiative heating processes that initiated the warming trend. The acoustic signatures of ice failure propagate through both the ice masses themselves and the underlying bedrock as pressure waves that can be detected across continental distances, creating a planetary soundscape dominated by the grinding, cracking, and collapsing of ice structures that have remained stable for geological epochs. The mechanical energy released during major ice failures exceeds that of large earthquakes, demonstrating the immense internal stresses that accumulate within ice masses during periods of thermal transition from frozen to liquid states. Subglacial water systems that have remained confined beneath ice for millions of years begin to encounter pathways to the surface as ice fractures create connections between the high-pressure water films that exist at ice bedrock interfaces and the atmospheric pressure conditions that characterize ice-free surfaces. These newly liberated subglacial waters carry dissolved minerals and organic compounds that have accumulated in isolation for geological time periods, creating chemical signatures that provide direct evidence of the geochemical processes that operated beneath global ice coverage. The albedo feedback mechanisms that maintain stable ice coverage for millions of years begin to operate in reverse as expanding areas of dark water and exposed bedrock absorb increasing quantities of solar radiation that would previously have been reflected back to space with minimal atmospheric heating. Each square kilometer of newly exposed dark surface absorbs enough additional solar energy to melt several square kilometers of surrounding ice, creating expanding zones of thermal influence that accelerate the overall deglaciation process through positive feedback effects. Atmospheric circulation patterns respond to the changing thermal characteristics of surface conditions by developing enhanced meridional circulation systems that transport warm air masses from newly ice-free regions toward areas that remain ice-covered. Distributing the thermal effects of initial ice melting across much larger geographical areas than would be affected by conductive heat transfer alone. These atmospheric heat transport mechanisms accelerate ice melting in regions that have not yet experienced direct thermal effects from greenhouse warming. The release of water vapor from melting ice increases atmospheric humidity levels that have remained extremely low throughout the frozen epoch, creating enhanced greenhouse effects as water vapor contributes its own infrared absorption characteristics to the atmospheric warming processes already initiated by carbon dioxide accumulation. The interaction between carbon dioxide and water vapor greenhouse effects creates amplifying feedbacks where each gas enhances the warming effects of the other through complex atmospheric chemistry and radiative transfer processes. Ocean currents that have remained dormant beneath global ice coverage begin to resume circulation as expanding areas of open water allow wind stress to drive surface water movements, and density differences between ice melt water and underlying oceanic water masses create pressure gradients that drive convective circulation. These renewed oceanic circulation patterns transport heat from equatorial regions that experience the most intense solar heating toward polar regions where ice coverage remains most extensive, accelerating the global deglaciation process. Biological communities that have survived in refugia throughout the frozen epoch begin to detect the chemical signatures of changing environmental conditions as increased atmospheric humidity and rising temperatures create conditions that approach the tolerance ranges for more active metabolic processes. These biological responses to improving environmental conditions provide additional feedback effects as increased biological activity begins to influence atmospheric composition through photosynthetic processes that modify carbon dioxide concentrations and oxygen levels. The structural integrity of continental ice sheets becomes compromised as thermal expansion and contraction cycles create fatigue effects that weaken the crystalline structure of ice masses, making them more susceptible to failure under the mechanical stresses created by their own immense weight. These structural weakening effects operate according to the same materials science principles that govern the failure of engineered structures under cyclic loading, demonstrating the universal nature of mechanical failure mechanisms across all scales from molecular to continental. Volcanic processes that have continued throughout the frozen epoch begin to interact more directly with surface atmospheric conditions as ice thickness decreases and volcanic heat sources approach closer proximity to ice-free surfaces, creating enhanced thermal effects that accelerate local ice melting while simultaneously increasing the efficiency with which volcanic gases reach the atmosphere without being trapped beneath ice coverage. The mathematical inevitability of continued warming becomes apparent as the physical processes that initiated ice melting continue to operate with increasing effectiveness, creating conditions where the transition from ice-covered to ice-free planetary conditions becomes self-sustaining through positive feedback mechanisms that operate faster than any possible negative feedback processes that might restore ice coverage. The planet commits itself irreversibly to deglaciation through the same types of threshold effects that originally committed it to comprehensive glaciation. Pressure release effects from ice unloading begin to influence crustal mechanics as the removal of ice masses allows crustal rebound processes to operate, creating additional mechanical stresses that contribute to ice sheet instability while simultaneously exposing new land surfaces to atmospheric conditions for the first time in millions of years. These isostatic adjustment processes provide additional mechanisms through which deglaciation accelerates once initial ice melting reaches critical thresholds. The Great Thaw begins with the inexorable logic of thermodynamics made manifest on planetary scales, as the albedo feedback mechanisms that once maintained global refrigeration reverse their operation with mathematical precision, transforming Earth's surface from a reflective white sphere that rejected solar energy into an increasingly dark world that absorbs electromagnetic radiation with the efficiency of a cosmic heat engine. Dark ocean water, newly exposed after millions of years beneath ice, absorbs 90% of the solar radiation that strikes its surface, converting light into thermal energy that spreads through oceanic water masses and atmospheric circulation systems with the patient inevitability of physical law operating across geological timescales. The acceleration of ice melting proceeds through positive feedback loops that demonstrate the same exponential characteristics that govern the original ice formation, yet operating in reverse to create warming effects that compound upon themselves with increasing effectiveness as larger areas of dark water become exposed to direct solar heating. Each additional square kilometer of open ocean creates thermal conditions that make the melting of surrounding ice more probable, while simultaneously contributing water vapor to an atmosphere that has become increasingly effective at trapping outgoing thermal radiation through enhanced greenhouse effects. Ocean circulation patterns that have remained dormant beneath ice coverage for tens of millions of years resume operation as expanding areas of open water allow wind stress to drive surface currents, and density differences between ice melt water and underlying oceanic water masses create pressure gradients that initiate convective circulation systems. These renewed oceanic currents transport heat from equatorial regions where solar heating operates most intensely toward higher latitudes where ice coverage remains most extensive, distributing thermal energy across planetary distances with efficiency that accelerates global deglaciation. The thermal capacity of oceanic water masses creates thermal inertia effects that initially slow the warming process, but eventually contribute to its acceleration as vast volumes of seawater absorb and store thermal energy that continues to drive ice melting long after atmospheric temperatures stabilize at their new equilibrium values. The oceans transform from thermal sinks that absorb heat during the initial stages of deglaciation into thermal sources that continue to release stored heat energy for thousands of years after the transition from ice-covered to ice-free conditions. Atmospheric humidity levels increase dramatically as melting ice releases water vapor directly into the atmosphere while simultaneously creating open water surfaces from which additional evaporation can occur at rates that depend on both water temperature and atmospheric circulation patterns. The enhanced atmospheric humidity contributes additional greenhouse warming through water vapor's strong infrared absorption characteristics, creating amplifying effects where increased temperatures lead to increased atmospheric moisture, which in turn leads to additional warming through enhanced greenhouse gas effects. The mechanical fracturing of ice masses accelerates as thermal expansion and contraction cycles create fatigue effects that weaken the crystalline structure of ice sheets, while simultaneously generating internal stresses that exceed the tensile strength of solid water when thermal gradients become sufficiently steep. These mechanical failure processes operate according to materials science principles that govern the fracture of all crystalline solids under thermal stress, creating ice sheet instabilities that contribute to rapid deglaciation once critical thermal thresholds are exceeded. Subglacial water systems that have operated beneath ice coverage throughout the frozen epoch begin to emerge at the surface as ice thickness decreases and hydraulic pressure gradients drive confined water toward atmospheric pressure conditions through newly created fracture systems and ice margin retreat zones. These emerging subglacial waters carry dissolved minerals and organic compounds that have accumulated in isolation for geological time periods, creating distinctive chemical signatures in newly ice-free oceanic regions. Biological communities that have survived in refugia throughout the global glaciation begin to expand their populations and geographic ranges, as improving environmental conditions create habitat opportunities that have not existed for millions of years. Yet their expansion proceeds slowly due to the limited genetic diversity and population sizes that characterize organisms that have survived prolonged environmental stress. These biological responses to improving conditions provide additional feedback effects as increased photosynthetic activity begins to modify atmospheric composition through carbon dioxide consumption and oxygen production. The geographical patterns of deglaciation reflect the complex interactions between solar heating, atmospheric circulation, oceanic heat transport, and local topographic effects that create spatial variations in the rate at which different regions transition from ice-covered to ice-free conditions. Equatorial regions experience the most rapid ice melting due to intense solar heating, while polar regions remain ice-covered longer due to reduced solar energy input and enhanced radiative cooling. To space during periods of seasonal darkness, volcanic processes that have continued throughout the frozen epoch begin to interact more directly with surface conditions as ice coverage retreats and volcanic heat sources achieve greater influence on local environmental conditions, creating enhanced geothermal effects that accelerate ice melting in volcanic regions while simultaneously increasing the efficiency with which volcanic gases reach the atmosphere without dilution or chemical modification by interaction with ice. The chemical composition of newly ice-free oceanic water differs significantly from that of typical seawater due to the concentration effects created by selective freezing processes and the absence of biological and atmospheric exchange processes during the frozen epoch, creating distinctive chemical environments that influence both biological colonization patterns and atmospheric chemistry as these modified water masses begin to interact with surface atmospheric conditions. Atmospheric pressure patterns respond to changing surface thermal characteristics by developing new circulation systems that transport heat and moisture according to the pressure gradients created by differential heating between ice-covered and ice-free surface regions, establishing weather patterns that differ fundamentally from those that characterized either the pre-glacial period or the fully frozen epoch. These transitional atmospheric circulation patterns help distribute the thermal effects of deglaciation across continental and oceanic distances. The rate of atmospheric carbon dioxide removal begins to increase as expanding areas of open ocean water provide surfaces where atmospheric carbon dioxide can dissolve into seawater, while simultaneously creating conditions where biological processes can resume carbon dioxide consumption through photosynthesis and other metabolic pathways that have operated at minimal levels throughout the frozen epoch. These enhanced carbon dioxide removal processes begin to moderate atmospheric greenhouse gas concentrations as deglaciation proceeds. The irreversibility of the deglaciation process becomes apparent as the physical mechanisms that drive continued ice melting operate with increasing effectiveness, while the mechanisms that might restore ice coverage become progressively less capable of overcoming the warming effects of reduced planetary albedo and enhanced atmospheric greenhouse gas concentrations. The planet commits itself to complete deglaciation through threshold effects that make the restoration of ice-covered conditions impossible without external changes in solar luminosity or massive volcanic cooling events. Rivers return to stone with the hesitant persistence of water rediscovering pathways that have remained frozen beneath ice for geological ages, as meltwater begins to carve channels through landscapes that have experienced no flowing water for millions of years, creating drainage systems that follow both the ancient river valleys buried beneath ice and entirely new topographic gradients created by the weight and movement of continental ice sheets. The sound of flowing water returns to a planet that has known only the silence of ice and wind, establishing acoustic environments that will eventually support the complex soundscapes of biological communities adapted to aquatic and riparian habitats. The erosional power of meltwater operates with enhanced effectiveness compared to normal river systems due to the enormous volumes of water released as continental ice sheets undergo catastrophic melting, creating flood events that transport sediments and dissolved minerals across continental distances in time periods measured in seasons rather than the geological ages normally required for such massive landscape modifications. These meltwater floods carve canyons through bedrock that has been exposed by ice sheet retreat, creating geological features that preserve evidence of the deglaciation process in rock formations that will persist long after the ice has completely disappeared. Sedimentary deposits created by meltwater transport accumulate in ocean basins and continental lowlands as distinctive geological formations that record the chemical and physical characteristics of the landscapes across which the meltwater flowed, creating archives of information about continental ice sheet composition, bedrock geology, and atmospheric conditions during the deglaciation period. These glacial sediments contain mineral assemblages and chemical signatures that differ from any sedimentary deposits formed under ice-free conditions, providing future geological evidence for the extent and characteristics of global glaciation. The chemical composition of meltwater reflects the accumulated effects of millions of years of rock-ice interaction beneath continental ice sheets. As dissolved minerals and organic compounds that have been extracted from bedrock through pressure melting and chemical weathering processes create water chemistry that differs significantly from typical river water in both mineral content and isotopic composition. This distinctive meltwater chemistry influences both the biological communities that begin to colonize newly ice-free aquatic environments and the ocean chemistry in regions where meltwater discharge creates large freshwater plumes. Waterfalls develop at locations where meltwater encounters abrupt changes in topography created by differential ice sheet thickness or bedrock resistance to glacial erosion, creating temporary but spectacular landscape features as enormous volumes of water cascade over ice-carved cliffs and through newly exposed gorges. These waterfalls represent transient geological phenomena that exist only during the active deglaciation period. As the landscape gradually adjusts to ice-free conditions and normal erosional processes resume their slower pace of topographic modification, the hydraulic energy of meltwater streams exceeds that of typical river systems by orders of magnitude due to both the enormous discharge volumes and the steep gradients that characterize freshly deglaciated landscapes, creating erosional processes that operate at rates comparable to those associated with major volcanic or tectonic events. This enhanced erosional activity rapidly modifies surface topography in ways that influence both local weather patterns and regional drainage basin development as the landscape transitions from ice-dominated to water-dominated geomorphological processes. Underground drainage systems develop as meltwater exploits, fracture networks and cavern systems that have been modified by millions of years of ice loading and unloading, creating complex subsurface water flow patterns that may transport water across continental distances before emerging at surface springs in locations far removed from their origins. These subsurface drainage systems influence both surface water availability and groundwater chemistry in regions that experience ice sheet retreat, creating hydrological conditions that differ from those that characterize either fully glaciated or fully ice-free landscapes. The thermal effects of flowing meltwater contribute additional warming to landscapes already experiencing atmospheric and radiative warming. as water temperatures that remain close to freezing nevertheless represent significant thermal energy input compared to the sub-zero temperatures that have characterized these landscapes for millions of years. The thermal mass of flowing water helps moderate local temperature fluctuations while simultaneously providing thermal energy that accelerates the melting of remaining ice in contact with meltwater streams. Biological communities begin to colonize meltwater environments as improved temperature and chemical conditions create habitat opportunities for organisms adapted to aquatic environments. Yet these colonization processes proceed slowly due to the limited dispersal capabilities of organisms that have survived the global glaciation in isolated refugia. The establishment of aquatic ecosystems in meltwater environments represents the beginning of biological recovery processes that will eventually restore complex ecological relationships to landscapes that have supported only minimal biological activity for geological ages. The seasonal patterns of meltwater discharge create annual flood cycles that establish new ecological rhythms in landscapes that have experienced no seasonal variation in water availability for millions of years. As spring warming creates peak discharge periods, followed by reduced flows during summer months when melting rates decrease. These seasonal discharge patterns begin to establish the hydrological cycles that will eventually support the complex ecological relationships characteristic of temperate and tropical aquatic ecosystems. Coastal regions experience dramatic changes in water level and salinity, as enormous volumes of fresh meltwater discharge into oceanic regions that have maintained relatively stable chemical composition throughout the frozen epoch, creating estuarine environments where fresh and salt water interact through mixing processes that establish new chemical gradients and circulation patterns. These coastal mixing zones provide unique habitat opportunities for organisms capable of tolerating variable salinity conditions. The mechanical effects of flowing water on ice-covered surfaces accelerate ice sheet retreat through both thermal and hydraulic processes. As flowing water provides efficient heat transfer mechanisms that can melt ice from below, while simultaneously creating hydraulic pressures that contribute to ice sheet mechanical failure. The interaction between flowing water and remaining ice creates feedback effects that accelerate the overall deglaciation process through multiple physical mechanisms operating simultaneously. Atmospheric humidity in regions experiencing active meltwater discharge increases significantly due to enhanced evaporation from flowing water surfaces and increased plant transpiration as vegetation begins to recolonize areas with reliable water availability, creating local climate modifications that can influence regional weather patterns and contribute to the establishment of precipitation cycles in areas that have experienced only sublimation and deposition of water vapor for millions of years. The establishment of permanent meltwater drainage systems creates geographical frameworks that will influence landscape evolution and ecological development for millions of years after the completion of deglaciation. As river valleys and lake basins carved by meltwater provide the topographic structure within which future geological and biological processes will operate, these meltwater-carved landscapes represent the geographical legacy of global glaciation, preserving evidence of ice sheet extent and dynamics in topographic features that will persist throughout subsequent geological epochs. The warm exhale begins as Earth emerges from its crystalline slumber into atmospheric conditions that will seem almost impossibly benign compared to the comprehensive refrigeration that has characterized planetary climate for 100 million years. Yet this transition toward warmth proceeds with the same inexorable patience that governed the original descent into global glaciation, demonstrating once again the geological timescales on which planetary climate systems operate when driven by the fundamental physics of energy balance and atmospheric chemistry. The planet awakens into a greenhouse world where atmospheric carbon dioxide concentrations have reached levels several times higher than those that characterize the pre-glacial atmosphere, creating thermal conditions that will support liquid water across all latitudes while simultaneously establishing the chemical foundation for biological innovations that will transform the history of life on Earth. Atmospheric temperatures rise to levels that not only prevent the reformation of continental ice sheets, but actively promote the rapid melting of any residual ice masses that persist in polar regions or high-altitude locations, creating a thermal environment where frozen water becomes thermodynamically unstable across the entire planetary surface for the first time in geological memory. The enhanced greenhouse effect operates through radiative forcing mechanisms that trap outgoing thermal radiation with efficiency that exceeds anything Earth has experienced during previous warm periods, establishing surface temperature conditions that support liquid water from the deepest ocean basins to the highest continental elevations. Ocean temperatures undergo dramatic warming as the thermal capacity of seawater allows oceanic water masses to absorb and store enormous quantities of thermal energy released through enhanced greenhouse heating and reduced ice albedo cooling, creating oceanic thermal conditions that approach those found in modern tropical seas across all latitudes, including polar regions. These elevated ocean temperatures support enhanced evaporation rates that increase atmospheric humidity to levels that further amplify greenhouse warming effects through water vapor feedback mechanisms, creating stable atmospheric conditions that make the return to glaciated states virtually impossible without massive external perturbations to the climate system. The chemical composition of both atmosphere and oceans undergoes fundamental reorganization as enhanced biological activity begins to modify carbon dioxide concentrations through photosynthetic processes that operate at levels of productivity far exceeding anything that existed during the frozen epoch, while simultaneously releasing oxygen at rates that begin to approach those that will eventually support more complex forms of aerobic metabolism. These biological modifications to atmospheric chemistry create feedback effects that help stabilize the warm climate state while simultaneously establishing the chemical preconditions for evolutionary innovations that depend on specific atmospheric composition ratios. Biological communities that survived the global glaciation in limited refugia begin to undergo rapid evolutionary diversification, as warm climate conditions and enhanced atmospheric carbon dioxide concentrations create environmental opportunities that favor both population expansion and genetic innovation through natural selection processes operating on organisms that have maintained remarkable genetic diversity despite prolonged environmental stress. The combination of improved environmental conditions and reduced competition from extinct species creates ecological niches that support evolutionary experimentation with new metabolic pathways, structural adaptations, and reproductive strategies. Continental landscapes that have remained buried beneath ice for millions of years become exposed to weathering processes that operate under warm, humid atmospheric conditions, creating enhanced rates of chemical weathering that begin to consume atmospheric carbon dioxide through rock-atmosphere interactions while simultaneously releasing dissolved minerals that increase oceanic nutrient availability and support enhanced biological productivity in marine ecosystems. These enhanced weathering processes establish negative feedback mechanisms that will eventually moderate atmospheric carbon dioxide concentrations and contribute to long-term climate stability. The absence of polar ice coverage eliminates the seasonal and annual climate variations that characterize ice-influenced climate systems, creating relatively stable temperature and precipitation patterns that vary primarily in response to solar angle variations and atmospheric circulation patterns rather than the complex feedbacks between ice coverage, albedo effects, and seasonal temperature cycles. This climate stability provides environmental conditions that favor the establishment of biological communities adapted to predictable environmental conditions rather than the extreme environmental variability that characterizes glacial-interglacial climate cycles. Oceanic circulation patterns develop characteristics that reflect the absence of polar ice coverage and the enhanced thermal energy available to drive atmospheric and oceanic circulation systems, creating global heat transport mechanisms that distribute thermal energy with efficiency that maintains relatively uniform temperatures across all oceanic basins, while simultaneously supporting atmospheric circulation patterns that transport moisture and heat energy across continental distances with unprecedented effectiveness. These enhanced circulation systems help maintain global climate stability while supporting biological productivity across all geographical regions. The elevated atmospheric carbon dioxide concentrations that characterize the immediate post-glacial atmosphere create environmental conditions that particularly favor photosynthetic organisms capable of utilizing enhanced carbon dioxide availability for increased growth rates and biomass production, leading to biological productivity levels that exceed anything that existed during the pre-glacial period and establishing the foundation for ecosystem complexity that will eventually support multicellular life forms of unprecedented size and organizational sophistication. Volcanic processes that contributed to atmospheric carbon dioxide accumulation throughout the frozen epoch continue to operate under the new warm climate conditions. Yet their relative importance in determining atmospheric composition decreases as biological processes become increasingly effective at consuming atmospheric carbon dioxide through photosynthesis and other metabolic pathways that incorporate atmospheric carbon into biological molecules and sedimentary deposits formed through biological activity. The geochemical cycles that operate under warm climate conditions differ fundamentally from those that characterized both the frozen epoch and the pre-glacial period due to the enhanced rates of chemical weathering, biological activity, and atmospheric oceanic exchange that result from elevated temperatures and atmospheric carbon dioxide concentrations, creating accelerated cycling of essential elements like carbon, nitrogen, and phosphorus through biological and geological systems operating in close chemical communication with each other. The establishment of stable warm climate conditions creates environmental opportunities for biological innovations that depend on chemical and physical conditions that have not existed since before the global glaciation, including complex multicellular organizations that require specific temperature ranges, atmospheric compositions, and ecosystem relationships that can develop only under stable environmental conditions maintained over geological timescales. The transition from the most comprehensively glaciated state in Earth's history to the most uniformly warm climate conditions the planet has ever experienced represents one of the most dramatic climate transitions in geological history, demonstrating the remarkable range of climate states that Earth's atmosphere-ocean ice system can maintain while remaining within the temperature ranges that support liquid water and biological activity across planetary surfaces. This warm exhale establishes the environmental foundation for the next major chapter in Earth's biological history, creating conditions that will eventually support the evolution of complex multicellular life forms while simultaneously demonstrating the remarkable capacity of planetary climate systems to undergo complete reorganization through the patient operation of physical and chemical processes operating across geological timescales. Memory in stone and time preserves the story of Earth's longest winter within geological formations that will endure long after the ice has vanished and the warm seas have given way to countless subsequent climate changes. Each rock layer, a page in the planet's autobiography of transformation, written in the precise chemical language of isotope ratios, mineral compositions, and fossil assemblages that record environmental conditions with accuracy that exceeds any human documentation system. The sedimentary deposits laid down during the transition from global glaciation to greenhouse warmth contain within their crystalline structures the chemical signatures of atmospheric composition, ocean temperature, biological productivity, and volcanic activity that characterized each phase of this 100-million-year climatic epic. Dropstones scattered through marine sediments tell the story of icebergs that drifted across tropical oceans, carrying fragments of continental bedrock thousands of kilometers from their origins before melting and releasing their rocky cargo onto seafloors that had never before received sediments transported by ice, creating geological anomalies that will puzzle future scientists until they reconstruct the comprehensive nature of global glaciation. These ice-rafted debris deposits preserve evidence not only of the extent of glaciation, but also of the geological composition of continents that lay buried beneath ice sheets, providing information about crustal evolution and tectonic processes that operated throughout the frozen epoch. The carbon isotope signatures preserved in sedimentary carbonates record the dramatic changes in atmospheric carbon dioxide concentrations and biological productivity that characterize the transition from frozen to greenhouse conditions. As the isotopic composition of carbon incorporated into marine sediments reflects both the atmospheric carbon dioxide levels and the degree of biological processing that modified atmospheric carbon before its incorporation into sedimentary deposits. These isotopic records provide quantitative measurements of atmospheric chemistry changes with temporal resolution that allows reconstruction of the precise timing and magnitude of environmental transitions. Banded iron formations that accumulated during the late stages of global glaciation preserve chemical evidence of ocean chemistry evolution as increased volcanic activity and reduced biological productivity created oceanic conditions where dissolved iron could precipitate in response to seasonal or cyclical changes in oxygen availability, generating sedimentary deposits with distinctive mineralogy and chemical composition that reflect the unique environmental conditions that existed during the transition from frozen to warm oceanic conditions. The thickness and geographical distribution of glacial sedimentary deposits provide direct measurements of ice sheet extent and duration. As the volume of sediment eroded and transported by continental ice sheets correlates with both the area covered by ice and the length of time that ice remained in contact with bedrock surfaces, creating geological records that allow quantitative reconstruction of ice sheet dynamics throughout the glaciation and deglaciation periods. These sedimentary archives preserve information about ice flow directions, ice sheet thickness variations, and the timing of ice sheet advance and retreat across continental surfaces. Paleomagnetic signatures contained within sedimentary rocks deposited during the global glaciation record both the orientation of Earth's magnetic field during sediment deposition and the precise geographical locations where sediments accumulated, providing information that allows reconstruction of continental positions and plate tectonic motions that occurred throughout the frozen epoch, while simultaneously establishing precise chronological frameworks for correlating geological events across different continents and ocean basins. The fossil record of organisms that survived global glaciation preserves evidence of biological adaptation strategies and evolutionary innovations that allowed life to persist through environmental conditions more severe than any that have existed during subsequent geological periods, demonstrating the remarkable resilience of biological systems and providing insights into the fundamental requirements for life persistence under extreme environmental stress. These biological archives also preserve genetic information that records evolutionary relationships between pre-glacial and post-glacial organisms. Chemical weathering products preserved in sedimentary deposits record the enhanced rates of rock-atmosphere interaction that characterized both the onset and termination of global glaciation. As the chemical composition of weathering products reflects both the intensity of weathering processes and the atmospheric composition that drove chemical reactions between bedrock and atmospheric constituents. These chemical signatures provide evidence for the atmospheric carbon dioxide concentrations that contributed to both glaciation onset and eventual warming. The mineralogical composition of sediments deposited in different environmental settings during the glaciation period preserves information about the specific chemical and physical conditions that characterized various depositional environments. From subglacial settings where sediments accumulated beneath continental ice sheets to deep marine environments where sediments recorded the chemical evolution of ice-covered oceans throughout the frozen epoch. Trace element concentrations in sedimentary rocks reflect the sources and transport mechanisms that delivered materials to sedimentary environments during global glaciation, providing information about atmospheric circulation patterns, oceanic current systems, and continental erosion processes that operated under environmental conditions significantly different from those that characterize more familiar geological periods, with extensive ice-free surfaces and active biological productivity. The stratigraphic relationships between different sedimentary units deposited during the glaciation period establish the temporal sequence of environmental changes and provide frameworks for understanding the causal relationships between different aspects of the climate transition, as the superposition of sedimentary layers preserves the chronological order of geological events with precision that allows reconstruction of the detailed sequence of processes that drove planetary climate evolution. Volcanic ash layers intercalated with glacial sediments provide chronological markers that allow precise dating of glacial events, while simultaneously preserving chemical information about volcanic activity levels and atmospheric chemistry during specific time intervals, creating temporal frameworks that connect geological events with climate changes and biological evolution throughout the period of global glaciation and subsequent warming. The preservation potential of glacial sedimentary deposits exceeds that of most other geological formations due to the rapid burial rates and reducing chemical conditions that characterize glacial depositional environments, ensuring that the geological record of global glaciation will remain accessible to scientific investigation throughout subsequent geological periods spanning hundreds of millions of years. These geological archives demonstrate that Earth's climate system operates according to physical principles that create predictable relationships between atmospheric composition, surface conditions, and biological productivity. Yet they also reveal the remarkable complexity of interactions between different Earth system components that can produce climate transitions spanning geological timescales and environmental changes that approach the theoretical limits for planetary habitability. The stones remember everything, holding within their crystal lattices and chemical bonds the complete story of planetary transformation, waiting with mineral patience for future investigators who will read these geological texts and reconstruct the epic of Earth's longest sleep and most dramatic awakening. Learning lessons about planetary climate evolution that apply not only to Earth's past, but to the climate futures of worlds circling distant stars throughout the galaxy. Wind down. In the silence that follows planetary awakening, the stones rest beneath warm seas that will never again know the comprehensive embrace of global ice. The memory of that 100-million-year winter becomes geology itself, written in the patient language of sediment and crystal, preserved in the chemical whispers of ancient atmospheres trapped within rock. Earth drifts onward through the cosmos, carrying within its geological heart the story of its most profound transformation, its journey from fire to ice to warmth again. The cycles continue, but none will match the scale of this ancient sleep. In every grain of sand eroded from those glacial deposits, in every fossil that records life's persistence through impossible cold, the planet keeps its deepest secrets. The warm exhale becomes a gentle sigh across time, as Earth settles into rhythms that will echo through deep time breathing with the slow pulse of continental drift, the patient accumulation of life's innovations, the steady clockwork of orbital mechanics that governs all planetary seasons. The ice dreams fade into stone dreams, and stone dreams fade into the endless dreaming of a planet that knows the mathematics of eternity. Sleep comes easily now, after such a long waking, after such a long remembering of what it means to be a world that can freeze solid and still find ways to bloom again. The story ends as all planetary stories do, not with conclusions, but with the quiet continuation of processes that operate beyond the measure of any single climate state, any single geological epoch, any single moment in the 4 billion-year conversation between matter and energy that we call Earth.